Hello everyone. So let's see how to solve this question. So this is this week's premium question for this month. So this question is maximum coins heroes can collect. Okay. So let's go through the question description once. So there is a battle and N heroes are trying to defeat M monsters. Okay. You are given two one index arrays of positive integers, heroes and monsters of length n and m, respectively. Heroes I is the power of ith hero and monsters I is the power of ith monster. So we will be given two arrays, and in that array, whatever the value is at the ith position, that value will be the power of the hero, or that value will be the power of that monster. Okay. So the ith hero can defeat the jth monster if monster j is less than equals to hero's I. Okay, so if the monster's power, so suppose if in this case, if I take this hero, the hero number one, so if this hero is having the power of one and this monster is having a power of one, okay, so then this hero can defeat this monster because this monster power is less than equals to the power of the hero. So hero can defeat this monster. So that's what this line is saying. So this can defeat. You are also given a one index array coins of length m consisting of positive integers. Coins I is the number of coins that each hero earns after defeating the ith monster. So suppose if this first hero defeats this first monster, then corresponding to this first monster, we have some coins with us. So if he defeats this monster, then he'll be getting this two coin. Okay. So this is the number of coins which he'll be getting on defeating this monster. So coins is the number of coins that each hero earns after defeating the ith monster. Return an array answer of length n, where answer is the maximum number of coins that ith hero can collect from this battle. Now we have to generate an answer array. In this answer array, what we'll be storing is that what's the maximum amount what's the maximum amount of coins this hero can collect after defeating the monsters. Okay, so let's go through this example also once. And before that, there are two more things to note. The health of a hero doesn't get reduced after defeating a monster. So our hero is very powerful. So this hero's strength is not decreased even after defeating any number of monsters. Okay, so the monster strength does not impact our hero's power. So if he defeats a monster, then also he's having a full strength. Okay, multiple heroes can defeat a monster, but each monster can be defeated by a given hero only once. Okay, so what this means is that this one hero, hero number one, which is having a power of one, can defeat this monster, and also this hero number four can also defeat the same monster. Okay, but the thing is that this first hero cannot defeat this monster again, so he can defeat it only once only. Okay, okay. So these two things are to be noted. So now let's go through the question description, like the answer. So how the answer is being generated for here is that this this first hero can defeat these two monsters. Why? Because these two monsters power is less than equals to this hero power. Okay, so these both are having one. So what's the corresponding number of coins to these? So this is 2 and 3. So this 2 and 3 gives us a summation of 5, and that's being stored at the first position. So this first hero can collect these many coins, these 5 coins. Okay. So then this second hero comes. So how many coins this second hero can collect? So he can defeat this one, this one, this one, and this one because all of them are having less than equals to power than our hero. So after defeating them, what will be the total number of coins? This will be 2 plus 3 plus 5 plus 6. Okay, 2 plus 3 plus 5 plus 6. So this is 5, this is 5, this is 10, this is 6. So this is 16. Okay, so that's why 16 is being stored over here. Okay. And similarly for the hero which is having the power of two can defeat this one, and this one only. So this is two and three. This is five. This is five. So this is 10. Okay. So that's why 10 is being stored. So how to solve this problem? Let's think. So one approach which comes to our mind is that we can just iterate over all the monsters. So for each hero, we can iterate over all the monsters and check like whether this hero can defeat this monster, this monster, this monster, and so on. And if this can defeat this monster, then we can just simply add in our answer. So, but when we will do that, the time complexity will be of somewhat of n square. Okay, and if we go through the constraints, the the hero's length is 10 to the power 5, and also the monster length is also 10 to the power 5. Okay, so this approach won't get accepted. So we need to optimize it, and we need to look for a better approach. Okay. So now, if we think about it more, so this hero, okay. So for a hero, what all monsters can he defeat? Okay. So this hero can defeat this one, this two, and this three. So like if I somewhat this just sort this up, if I somehow sort this up, then after a point, if suppose if I will be getting after sorting this out, I can get 1, 1, 2, 5, 3. Okay, this is the okay, not 2, 5, 3. This is 2, 3, 5. Okay, so this is the sorted array. Okay, so suppose if I am checking for this first hero. Okay, so after checking for the first hero, I can start from here. Like I can go to here, 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 and once I reach over here, I can see this monster power is greater than my hero power. So moving forward also, all the monster power will be greater than my current hero's power. Okay, so no use of moving forward. So this sorting can help us. Okay, this sorting can help us in optimizing like till how many monsters I can defeat. Okay, so in that this sorting can somewhat optimize things up. Okay, but still, when I'm if I even after sorting this monsters array, even if I iterate on this, then also the time complexity will be of n square only because we are just not like we are just iterating over this whole array only. So for each monster, I am iterating over this array again. So, but once we have it sorted, what we can do, we can apply binary search. Okay, we can apply binary search on it because if I am over here is standing at some position. Okay, so binary search is on a sorted space. Okay, so we have our sorted array. So if I can defeat a monster at this position, then I can try to further like increase my search space on this side. Like I will try like if I can defeat more monsters, and if I cannot defeat this monster, then that's for sure that I won't be able to defeat these monsters also, and I need to reduce down my search space. Okay, so that's how I can reduce down my search space, and I'll be checking on left hand side of the things. Okay, so that's how binary search can help us. So when we'll be performing binary search, we will be looking out for the last monster which I can defeat. So for the first hero, the last monster which I can defeat will be this one. So this is the last monster which the hero can defeat. Okay. So we will be applying binary search. So then that binary search, what that will do for us is that that will reduce our inner time complexity of our inner loop from O of n to O of log n. Okay. Okay. So now we are somewhat at n log again. So we are going good. Okay. So things are going fine. And so if I can apply binary search, I can get the last position. That's not a big deal. But there's one more thing. If you note, like if I just sort this array out, then the corresponding mapping of these coins will be lost. Okay. So this monster, okay. So as you can see, if you take this index, okay. So for this index, this five monster, the monster with the health of five, previously the coins was four. Okay, okay. But now if I check in this new array, if I just directly go and check, then that will give me six. Okay, so that's not right. So we need to bind them down with each other. Okay, so these need to be binded together. Okay, so we can create some pair class like thing. So these two can be binded together, and then we can search out for the then we can search out for the last position of the monster which we can defeat. Okay, so now even if we have found the last position, so we can find the position in log n. Okay, the last monster which is defeated. But there's one more thing. One more thing which is there is that even if I have found out the last position of the monster, I still need to figure out the sum of all the monsters till that last position. Okay. So if I just iterate over them, then that will be a O of n. So outside O of n loop and again O of n loop. So whatever help we got from binary search, that will be wasted again. So we cannot again iterate over all the positions from zero till the last monster position. Okay. So we need to reduce the time complexity of this as well. Okay. So now how can we reduce the time complexity for this? That is, if we just take the prefix sum, if we take the prefix sum from beginning. Okay, so how the prefix sum will be taken is that, so prefix sum for this we can take as like for this coins array. Okay, so because we need to know from which, from starting to the last monster which I am defeating, from starting to that last monster position, how much the total coins I can get. Okay, so, so I have just created the mapping for this. So this monster is having this coin, this monster is having this coin. So now we need to do a prefix sum of this on this coin. Okay. So if you take the prefix sum for this coin, what will be the prefix sum? That will be 2, 5, 10, and 16, and then 20. Okay. So now if you see, so this first hero is having a power of 1. Okay. So this can defeat till here. So till here, what is the prefix sum? What's the prefix sum is 5. So see, we just directly got the answer as 5. We can just directly get the answer as 5. This will be pre-computed before. Okay. So I directly got the answer 5 for this. Then I will check for this again for this hero which is having a power of 4. So this hero can defeat till here. Okay, till this 3. Okay, so this will be getting the reward of 16. Okay, so see, we have just stored the total sum of the rewards, so the total coins which I can get till this monster position. Okay, so this is helping me to just directly get the result in O of 1. For similarly, we can check for this hero which is having a power of 2 also. So so this hero which is having a power of 2 can defeat till here. So the answer will be 10. Okay. So now we have talked a lot about the approach. So now let's just see the code. So in the code, what I have done is in the code I am just creating a monsters array. Okay. So as I told you earlier, we need to store this mapping because when I'll be sorting this monster's power, when I'll be sorting this power, these mappings will get affected. So I need to bind them together. Okay. So for binding them, I have created a monster class. So this monster class is having two properties, monster power and monster defeat reward. Okay. So this is the class. Okay. So these two properties I am binding together. So what I am doing over here now is that I am just creating a monsters array, and after iterating over all the monsters, I am storing their monster power and their coins together. Okay. So now after that, what I have done, I have sorted all the monster power because that will help me to just directly perform binary search. So I can perform binary search on the sorted array. So that will give me the last position of the monster which I can defeat. Until there I can get the reward sum. Okay. So then I have taken the prefix sum in this array. This reward sum is nothing, just the prefix sum array. Okay. So what I have done is for prefix sum, this is the standard prefix sum code. So this reward sum I is just storing the reward sum till I minus 1 and also adding the reward of this monster. Okay, so whatever the reward was till this position, I am just adding this coins of this monster also. Okay, this is just a standard prefix sum. You can have a look at this code and you can get to know this is nothing much over here. So then I have just created the resultant array in the hero coins, which I'll be returning in the end. So whatever the hero coins which we'll be getting over here. So then I am just iterating over all the heroes. So for all the heroes, I am just fetching the hero power. Once I have the hero power, for that I'm calling this function find last monster to kill. In that function, I'm passing the sorted monsters, and I am passing this hero power. Okay, so let's see how this find last monster to kill function is there. So see, this is also just simple binary search. This is the starting position. This is the ending position. So if I see on the mid, if this mid is having the power less than equals to hero power, then I can defeat this monster. So basically, I need to check forward, and this can also be my answer. So, but suppose if I after this I don't get a further monster which I can defeat, so this can be my possible last monster. So I am just showing the last monster over here, and I am increasing my search is space to look from over here to end. Okay, not this side, just to look from here to end. Okay, so after this, this is just end array. This is just end pointer. So this end pointer is decrementing when I am not able to defeat this monster. Then obviously I won't be able to defeat the further monster. So this search space will be reduced. I'll be just needing to search over in this part. Okay, so that's how I'm just doing. I'm just is showing the last monster. So once I have this last monster, if suppose my hero was not able to defeat any monster, then I'm just returning a -1. So when I'll be getting a -1, so as my hero wasn't able to defeat any monster, so the answer for that hero will be 0. And as the or else this will be just the cumulative sum till the last monster position. Okay, so that's how I'm doing it. So yeah, that was the whole approach, and that's about it. So the time complexity we have already discussed. This is a n log n. Sorting is n log n. This is O of n. This is O of n times this log n binary search. This is n log n. This is also n log n. So n log n plus O of n plus n log n. This is n log n only. O of n log n is the time complexity. What's the space complexity? We have taken this reward sum array. So the space complexity will be O of n. Okay, because we have taken this reward sum array. So yeah, that's what it. I hope you like the solution explanation, and I hope I was able to make you explain the whole logic, the thought process. So yeah, that's about it. If you like the video, do consider subscribing to the channel. So yeah, thanks.